whenever you go last in the conference, it can be a bit tricky because I know that everybody's probably got flights to catch and everybody's falling asleep, and hopefully we can manage to keep everybody awake for the next 45 minutes or an hour or so. So let's crack on. Quantum computing. So first of all, just to introduce myself, I'm James, and I work for ThoughtWorks. I'm a lead developer at ThoughtWorks, which kind of means that I used to be a software developer, and now I organize software developers. And I do a lot of this stuff, which is great fun. ThoughtWorks pays me to come and talk at conferences. If you've never heard of ThoughtWorks, I'm supposed to show these slides. ThoughtWorks has been around for 25 years, and we're a consultancy. I think you may have heard of some of these people, some of these books. I know some of the people that have written some of these books. All of these were written by thought workers, some of whom are still at ThoughtWorks, some of whom aren't. I think Sam Newman's on here somewhere. Yeah. Oh, there you go, building microservices, yeah. But he left ThoughtWorks before I started. So I got to Porto yesterday, and I have to say it's a very beautiful place. I don't know if anybody in here is from Porto, but yeah, good. I thought there might be some. Lovely town. I don't quite understand why all this art is going on. There's an art thing going on here, which is great fun. This is in the hotel we're staying at, and I think the conference was trying to play some sort of sick joke on me. When I got into the hotel lift, I noticed that not only does it not have a 0, the ground floor is numbered 1, but there's a -1. So I was like, there's some sort of void in there somewhere, and I thought, my God, you know, that they can't even give us a 0-based lift system, which really, you know, for a technologist, I thought was a bit weird. Now, this scares the hell out of me. In the UK, there aren't many trams. That's a tram on a pavement. And yesterday, I heard the noise behind me, and I jumped out of the way into a car that was coming along the road. I was like, what the hell am I supposed to do? And if you look closely, there's a bloke hanging onto the side there. What on earth is that all about? And it really scares me, even though this is where I live, a place called Hemel Hempstead in Hertfordshire, just outside of London. This is a roundabout which is quite famous, and if you look closely, you'll notice that cars go around it in both directions. Now, I'm used to that, and yet the trams really scare me. And then yesterday, of course, I got to this place for this conference, and then, thank God, the lift is 0-based in this place. And that made me feel a lot better about the conference. And I didn't know about PubConf until yesterday, and I have to say that was one of the most entertaining hours or so of my life. It was fantastic. So if anybody here that spoke yesterday, that was amazing. And then, of course, it got dark, and just like pretty much every other conference I've ever been to, I woke up this morning and found a random selfie with people that I really don't know who they are. But they were very nice, I'm sure. So, what am I going to talk about today? Quantum computing. Does anybody in here use quantum computers? Anybody program quantum computers? A little bit? Yeah, okay. I'm going to talk about why I'm talking about quantum computing, the difference between what we're calling now a classical computer and a quantum computer. Then I've got some demos, which I call Clementines Cat, more of that later. Then I'm going to talk about what quantum computers are being used for, what they will be used for. And then I'm going to end with something called Shor's algorithm, which you may or may not have heard of. So, why am I talking about quantum computing? So, it's a good question. About this time last year, I was at a conference in Vienna, and I saw this talk. This man here is called Alistair Collinson. He's now a very good friend of mine. He gave a talk on quantum computing. I'd never heard of it before this point. I think I'd heard of it, but didn't think it was a real thing. I totally didn't understand any of it. And then I tried to talk to Alistair afterwards to understand a bit more, and he was a bit difficult to talk to. So I went away thinking, well, you know what, maybe I could do a better job of explaining this to beginners, because my feedback to him was I think the level was a bit too high. It went over everybody's head. I could see people busily Googling stuff during his talk. And here's me at the same conference making a joke at Alistair's expense. Apologies, Alistair. So after that conference, I put in a talk to another conference. I was invited to a conference in Poland, and they said to me, can you just give us a couple of talks to choose from? So I thought, OK. My usual talk at the time was this thing about microservices, and I put just this, thinking, well, they won't want me for the quantum thing because they had Alistair to talk about that. And then, of course, the microservices talk was rejected, and the quantum talk was accepted, which made me feel kind of like this. So what did I do? I then had to learn quantum computing in a couple of months, which was really hard. And the first time, well, I had to try. I went to a load of meetups. This was at Microsoft. This is Dr. Julie Love. She's head of their quantum science thing. She was talking about a new type of qubit, which I won't go into the details of. And then ThoughtWorks got wind of the fact that I was talking at a conference, and the global leadership team asked me to create the ThoughtWorks global strategy for quantum, which I still don't know what that means, to be honest. But I'm trying to raise awareness of quantum stuff. I've run quantum meetups now. And a highlight of that was last year in October, we had a Quantum Hack Day in London, which we're repeating in May, if anybody's interested, quick plug there, where IBM have given us exclusive use of their real quantum computers to submit quantum scores to, and we were running these quantum simulations. And that was amazing. And then at the end of last year, I don't know if you've heard of the ThoughtWorks Tech Radar. Q# has appeared in the assess ring of the Tech Radar. The guys asked me to write the blip, you know, so that was good. So it's coming. And that's so far what I've done. So this is why I'm talking about quantum. I'm trying to raise awareness of it and trying to get ThoughtWorks interested in actually understanding quantum so that we can lead the way in this technology, so that we can have consultants ready to program the quantum computers when they become a viable proposition, which is proving a difficult thing to do. Anyway, let's talk about quantum computers. I'm guessing most of the people in this room understand how a classical computer works, largely. So a classical computer basically stores zeros and ones. That's called a bit. And that thing there is a little logical diagram. I think that's called a flip-flop circuit. The current goes in and it flips. So classical computers typically store a 0 or a 1 as two different voltages, as I understand it. They have a thing called logic gates. There's an OR gate there, another schematic of an OR gate. Either A or B or both are closed, then the circuit goes and the light bulb lights up. Now this thing down here is a schematic of 16-bit floating-point arithmetic. And my reason for putting that there is you can see that all of these are logic gates. They all get aggregated together to do something useful. And that's, as I say, that illustrates 16-bit floating-point arithmetic. That is all classical computers do. They don't do anything else. They just put bits through logic gates. And an important thing to understand about classical computers is you can assume that there is no loss of information at any point through the logic gates. They're pretty much error-free in that respect, to all intents and purposes. Now, there's something called a qubit. This is the quantum analogy, the quantum thing that is like a bit. So qubit, quantum bit. Just like a classical bit, if you read their value, they will always give you just two distinct values, which we would always just refer to as 0 or 1. However, they are actually holding a lot more state than that at any given point. This is the piece where you have to start suspending your belief. If you've studied quantum physics, you'll probably take this a bit better than I did at the time. They can be in a pure position of 0 or 1, which means that if you measure the value, you'll get a 0 or a 1 with 100% certainty. There are lots and lots of other intermediate states. What is effectively happening in a qubit is that it's a point in a four-dimensional vector space is how you can think of it. The maths are there. If you read this Wikipedia article, it explains the maths behind it. But just trust me on that. And one thing, probably the most important thing, is this. In all but the most simple states, every qubit in the machine is holding a 0 and a 1 at the same time. So what that means is that you get a supermassive parallelization of computation. Now, I will demonstrate some of that later. For the time being, we just have to trust me that this happens. If you want to understand a bit more about the qubit, there's this representation of a qubit. This is called a block sphere. You can think of the state of the qubit as being a point on the surface of this sphere. Okay? If the point is straight up there, it will return a 0 with 100% probability. If it's pointing straight down, this arrow thing here, you'll get a 1 with 100% probability. Every other state that the qubit can be in, it returns what they call a probability space. So the probability, if it's up there somewhere, it's more likely to return a 0 than a 1 when you actually observe the value. Okay? So the way that the quantum computers work is that you put together a load of these qubits, and they all hold these states, and that enables you to actually, the block sphere is a good representation of a single qubit, but the picture breaks down when you have multiple qubits, because actually you start then actually getting a multi-dimensional hyper sphere type thing, which is impossible to visualize. If you are really interested, this talk here from Skills Matter, a friend of mine in London, really explains the maths behind the block sphere, why that mapping works. I don't have time to do that. So, you have a load of qubits in your quantum computer. What else do quantum computers do? Well, like classical computers, they have quantum logic gates. And what those logic gates do is they transform the state of the qubit in one way or another way. Some of them are pretty simple. You have X gates, which effectively, if you go back to this picture, they flip this pointer through 180 degrees with respect to one of the axes. And then the ID gate does nothing, as you'd expect. And then these are the more interesting gates. H is the Hadamard Gate. Now, what the Hadamard Gate does, and it's really important in quantum computing, is it flips the state round from being basically exactly halfway between 0 and 1. Okay, it's named after a guy that was around in the 1930s who did this using electrical circuits. And what the Hadamard Gate does is it puts your qubits into a superposition state. And I'll show you later exactly what that means. Don't worry too much about these. Yeah, the IBM Q Experience, I think I'm out of date there. When I wrote this slide, there were 13 gates in it. I'm going to show you the IBM Q Experience a bit later. That block sphere is just a single representation of a qubit. If you want to understand a bit more about how the qubits work and how the maps work, oh God, where's my mouse pointer? Here we go. There is an app called Hello Quantum, which is an IBM app. I met the man that wrote this app, and I'll just show it to you. This is on my phone. What this is, it's like a little puzzle game, and you can flip the state like this, and gosh, I don't know. There you go. And then it moves on to more complex problems, starts introducing more types of gates. So this is quite a useful little tool to try and understand how the transforms work. I'm not going to go into any more detail on that. Let's get rid of that chap. So yeah, that's called, Hello Quantum. So you can go and download that on the App Store. I think it's available on iOS as well. This is the bit where we find out that, here we go. Just very briefly, these are the important concepts that quantum computers use. Entanglement is when two qubits are linked in a way that measuring the value of this tells you something about the value of this one. Okay? And that becomes very important when you start writing quantum circuits. Something that else, which is similar to a classical computer, all the operations that you put into your quantum computer can be controlled by a qubit. So you can do something called a C0 gate, which is where, given the value of this, it might flip the value of this. So if the value of this is 1, it'll flip the value of this one. If the value of this is 0, it'll leave the value of this one alone. Now, the reason why that's important is because if your control qubit is itself in a superposition, then the computer will actually both execute and not execute some code. And you can use that property sums up in a way that becomes really important later. And quantum computers are provably, God, I can't remember the name, they passed the Turing, is it the Turing test? The Turing's theorem for being a universal computer, which means that every action actually can be undone. Part of that condition is that everything has an adjoint, which is what that means. And again, that becomes important later. Not quite sure what that link is. yeah, I do have that link. Oh, apologies, it's off the bottom of the screen. It's off the bottom of my screen too. Okay. So finally in this section, why would I want to use a quantum computer? What's the difference between them? Well, as I said, each qubit is effectively holding a value in four-dimensional vector space. So if you get 100 qubits, you've got something like, you've got exponentially more information in 100 qubits than you have in 100 bits. And you've got that information simultaneously. So the power is mind-boggling of what you can do with these quantum computers. And what they've actually done, provably, there are problems that will never be solved in classical computers that will be solvable in polynomial time in quantum computers. And I've got an example of that later. There are some disadvantages. As soon as you read the value of the qubit, all of that extra state information that it has collapses and goes away. It's lost forever. Now, what that means is that there is no useful way to persist the state in a quantum computer. Because to persist the state, you would have to copy the state. To copy the state, you'd have to observe the state, and you'd lose all that extra state information. So there is no concept of saving information or persisting information. Currently, the physical limitations of the hardware limit the breadth and depth of programs. What do I mean by that? At the moment, qubits are inherently unstable. Every time you put a qubit through a gate, it leaks some information into the gate, and the gate leaks some information into the qubit, and the nice state that we saw on the block sphere becomes degraded. So at the moment, there is a physical limit on the number of operations that you can use for your quantum computer, and that's very limiting. And finally, they're hard to program. I naively thought a year ago that I would just be like learning a new computer programming language. But actually, as I'll show you, you have to, Microsoft has started building some libraries with some useful abstractions, but in order to even understand those useful abstractions, you've really got to understand some of the quantum physics. And I'd never thought this would happen to me, but I've started reading books like this, which is called Quantum Mechanics, the Theoretical Minimum. And there's about 4 bookmarks in it. I'm reading it at different paces at different times, and I'm trying to use this information to build my own quantum computer, my own quantum simulator. So they're hard to program. So I'm going to show you some programs. Clementines Cat. Right. First of all, I'm going to show you the Ibm Q Experience. Has anybody used the Q Experience at all in this room? No hands? Okay. Okay. I need, where's my mouse pointer? How do I do this? This is the bit where I can never remember how to, right, I need my settings, don't I? System. Oh no, hang on a minute, sorry. This always happens to me. I can never remember, right, Q Experience. Let's minimize that. Can I put it over onto that? Yeah, here we go. Right. Oh, you know what? I've done the wrong thing. just bear with me a moment. I apologize, everybody. Oh, God. I'm trying to do the thing where the system preferences. I want to share my screen. So, displays, arrangement, mirror displays. There we go. Okay. This is the Ibm Q Experience website. Okay? I have an account on here. Anybody can set up an account. You can get a free account on the Ibm Q Experience, and this allows you to write quantum programs. Now, this is the first thing that I did to try and understand quantum programming. You can see here, this area of the screen, this is called a quantum score because it looks a bit like musical notation. Each of those horizontal lines represents a qubit. You can see up here, this is the physical representation of the computer. The IBM has 2 quantum computers, one called Tenerife, one called Yorktown. And I think at any given point, one of them is normally in maintenance. I don't know what that means, but the physical architecture of the chip is there. It has 5 qubits, as you can see, and those are the 5 qubits represented there. Now, the way this works is pretty simple. Let me just, you drag and drop, so I can put an X gate on that. I can put an X gate on that. And I can do things like this. I can then measure that qubit's value. I can measure that qubit's value. And I can measure that qubit's value. And I'm going to simulate this. I'm not going to run it for real because it will go into a queue and take ages to get to the front of the queue, and it will use up some of my credits. So if we just go simulate, we'll see what we get out. You see there, what it's actually done is it's run that quantum score, I think, 100 times, and it's telling us that 100% of the time the output is 00011. Okay? Now the reason why it's 00011 is because, well, for some reason that I still can't get my head around, that representation is the wrong order. It's the 4th qubit is the first one, and the 0th qubit is the last digit. Because I put the X gates on there, it flipped the value from being 0 to being 1. Okay? So that's pretty simple. We can see that that's just done something deterministic. Okay? Now, what I'm going to do is I'm going to show you what happens if I introduce a Hadamard gate. So I'm going to put a Hadamard gate here. So what we've now done is those first 2 qubits will always be 1. Now the 3rd qubit, some of the time when we observe the value, it's going to be 0, and some of the time it's going to be 1. So we just simulate that. And you can see that 54% of the time it was 1, 46% of the time it was 0. That's kind of what you expect. So why is that useful? Well, what I'm now going to show you, okay, so just before I move on, this also has a scripting language. I think it's Python-based. I'm not a Python person. If anybody knows Python, you can probably confirm whether that looks like Python or not. So that's a way that you can actually persist your code, write your code somewhere else, and then submit it to this computer. This is what we were doing when we did the hack day. We were writing the code, outside of this and then submitting it into the IBM system. What this also does is it allows you to save your quantum scores. So if we come down here, you can see I've got a load of stuff saved. Have people heard of Schrodinger's cat? Yeah. So Schrodinger's cat was a thought experiment by Erwin Schrodinger, which he was using to illustrate the absurdity, as he saw it, of the Copenhagen interpretation. And the story goes, okay, imagine a cat in a box. There is a radioactive isotope in this box with the cat. After a certain amount of time, the probability of the decay having happened is exactly 50%. If the decay happens, there's a Geiger counter which is linked to a little hammer which breaks a vial of cyanide gas, and the poor cat dies. Now, this here, I can show you now. There's a way that I load. Hang on a minute. Here we go. No. Oh, there it is, yeah. Which one do I want? I want, that's January. Oh, that's an interesting circuit, but I don't have time to go into that one. Okay, let's load one of these Schrodinger's cat circuits. Load it in the composer. Now, what we're using here is, this is a Hadamard gate. That represents, so that qubit is representing the radioactive isotope. If it decays, this is a C0 gate. So if the value of this is a 1, it will flip the value of Q2 to 1. So this represents the hammer. This represents the vial of poison, whether it's broken or not. And this represents the cat, so whether the cat is alive or dead. These 4 qubits are entangled by the C0 gate. So you can probably see that if the radioactive isotope decays, everything else will have a value of 1. Now, if we simulate this now, what we'll see is two results. They're either all 1s or they're all 0s. Now, that makes logical sense, I'm sure, to everybody. right? So that the radioactive decay happens, the cat dies. So all four things have happened. But that's a simulation. And just before we leave this, I'm trying to find my earlier, okay, Schrodinger's cat. Here we go. Yes, down here, this is a circuit, and I submitted these to the real quantum computer in October of last year. Now, I can show you the results of what happened because it's quite interesting. If we have a look at this one, no, not that one, that's a simulation. Not that one. Here you go. Now, this is what happened when I ran this against the real IBM quantum computer. In this one here, 37% of the time, the radioactive decay didn't happen, the hammer didn't move, the vial of poison didn't break, the cat didn't die. 29% of the time, the exact opposite happened. The radioactive decay happened, the hammer moved, the thing broke, the cat died. All of this stuff in the middle is an illustration of why quantum computers aren't yet ready for commercial stuff. Those are all errors. Okay, that is where the computer hasn't been sufficiently good at retaining its coherence. So I like this as a demonstration of the state of the art, really, of IBM's computer at the moment. I think it's improved since then. Like, from what I'm told by IBM, they're constantly improving it. But this is a pretty good illustration of why it's not quite there yet for us. So that's the IBM kit. Let's go back to my presentation. Okay, what's next? Yes?
Would you say that IBM's state of the art is the state of the art at the moment? Are they kind of the...
It's the only one that is readily available to use, but Rigetti, a company called, I've got a slide later, Rigetti probably have a better computer, and I think there's lots of secret computers in the world that we don't know about. So, I don't know why that is there. How do I get rid of that? Go on, get out of the way. Right. Okay, next, what am I going to talk about? Oh, God. I hate it when this happens. Right, so the mouse pointer has to be there, doesn't it? There you go. Why am I showing you this picture? This is the shower in the bedroom of the hotel that I'm staying. Now, you'll notice that there is a slight difference in the position of the temperature control. Now, what this is illustrating is something that I'm going to call Cooper's Law, named after Ian Cooper, because he mentioned this to me yesterday, and I told him I was going to work it into the presentation and write a simulation of it. Cooper's Law states that hotel showers have about 5 degrees of freedom on the little dial thing. And between those two settings, that is the only survivable temperature that you can get the shower to go to. Slightly to the right, the temperature of the water will be hotter than the center of the sun. Slightly to the left, it will be colder than outer space. That is called Cooper's limit. So, what I'm going to do now is very quickly demonstrate a quantum program in Microsoft Q# to actually write Cooper's limit. I did write this earlier. The chances are that I'll probably muck it up now. So, I have something here installed. There's a link on the next slide to the Microsoft Quantum Development Kit. There is a completely new language they've written called Q#. And you use Q# to write quantum programs. So, I should have in my command line here, there you go. Oh, sorry. Nobody's seen my screen. Mirror displays. Okay. Where's my console? No, that's not my console. There you go. How readable is that? Not very. Okay. Does anybody know how I could make the text bigger? Does that work in... Oh, yeah, lovely. Thank you very much. Right, is that readable? So, .NET new console minus lang Q# minus output shower simulation. So that's going to create a new There it is. I can now cd into that folder and launch MS Code. Here it is. Everybody familiar with this? This is the free version of Visual Studio. What's it done? Well, yes and yes. Again, is Command plus going to be my friend? It is. It has created a solution for me. It has 2 files in it. One is a C# file, and one is a Q# file. Okay? Now, what this is the C# program is needed to run the quantum program. And this is how it's effectively, that's how it's always going to be. You need some kind of interface between your classical computer that controls the quantum computer. So there's always this thing here, which is a driver, and then this thing here, which is the quantum code. So in true Blue Peter fashion, I did do this earlier, and I know that if I try and type it from scratch, I will get it completely wrong, so I'm not going to attempt that. So I will go through the code. First of all, here we go. This is Q# code. I think it's relatively easy to read. All we're doing here is, so I'm saying this is, hang on, my operation, bear with me, needs to return something. Maybe I'll just go to this one. Yeah, let's go to this one. So this is the version I wrote earlier, just for expediency's sake. So what's going on here? So we've got an operation called shower experiment. It takes a count, which is, this is a pretty common pattern in quantum computing. I'm going to execute the simulation a lot of times. And it returns 2 Boolean values. It's pretty simple. You instantiate 2 qubits there. Qubit 0 is representing the temperature of the water in the shower. Qubit 1 is representing the state of the person, the unhappy person that gets into this shower. So this thing here, H, this applies the Hadamard transform to the first qubit. So that means it's going to be cold with 50% probability or hotter than the center of the sun with 50% probability. And we're entangling the qubits with the C0 operation. So if the first qubit returns a 0, the second qubit will always return a 0. And similarly, if the first qubit returns a 1 when you observe the value, then the second qubit will also return a 1. Those 2 qubits are entangled now. And then we're simply measuring the result out. Okay? So, and I'm converting using, this is pretty crappy syntax, I've got to be honest, but I'm converting the value to the 2 Boolean values and then returning it outwards. Okay? And if we look in my driver program, what's happening in the C# side? By the way, my GitHub, there's lots of examples. You can download them. I've got a GitHub link later. This is not on GitHub yet because I did it this morning. You created the quantum simulator there. Now, Microsoft doesn't have a public quantum computer at the moment, so you have to use the quantum simulator. But their plan is, obviously, at some point, this line of code will be replaceable by a thing that instantiates an instance of this quantum computer in the cloud that doesn't exist yet. So we can currently write programs using Q#, and this is a lot of what I'm doing in my job at the moment, is trying to understand how to write useful programs. And then I'm simply saying, right, I'm going to run the experiment 100 times, and shower experiment.run, and all I'm going to do is just basically output whether the temperature was hot or cold, and whether the person is alive or dead. And let's see what happens if I run that program. Well, hopefully it's going to build and run for me. So let's go .NET run. We should just see a load of outputs. And there you go. And the purpose of this illustration is the fact that you can see that we're just getting pairs of trues or pairs of falses. So those 2 qubits are entangled, right? You can't get a false true. Although, as we saw with the IBM real quantum computer, if you ran this against a real quantum computer, you probably would get some false true stuff. So that's a very simple explanation of, and yes, sir?
Yeah. Is it only because we're in the early stages of quantum computing, or is the idea that when quantum computers are going to be available,
Yeah.
that the programmers, the developers are going to be using the gates direct result?
Yeah, I'm not quite sure I understand the
Is there going to be a more abstract, a more easier
right.
to read language?
Okay, the question is, will there be a more easy to read language? So this Microsoft kit has quite a lot of library functions in it for things like the quantum Fourier Transform and certain other quantum operations. So they are starting to do that. There is a company that I know of in Cambridge that is writing a quantum compiler. Now, the idea with a quantum code compiler would be you would write a single program, and the compiler would understand which bits to submit to a classical computer and which bits to submit to the quantum computer. But that's all coming. But Microsoft believe that this will be the solution, right? So, and I like using Microsoft Toolset. I mean, I know I get shot within ThoughtWorks for saying this, but I think Microsoft tools are fantastic. And this Q# I find really accessible. But as you've probably pointed out there, you do need to understand what's going on. At the moment, you need to program at the level of the qubits and the gates. And that's what pretty much is going on. But I have some more complex demos, which I'm going to move on to. So I mentioned Clementines Cat. Let me just tell you a quick story. Not quite sure. Oh, here we go. So, what's Clementines Cat? So, this is me with my older daughter, Clementine. That's Clementines Cat. Now, the reason why I decided to write a story about Clementines Cat was because I told my daughter the story of Schrodinger's cat, this Clementine, and she said, "Daddy, why would anybody do that to their cat?" And I was like, well, no, he didn't actually poison his cat in a box, or at least not to my knowledge. So I wanted to write a more humane version of the thing. So just for balance, there's my other daughter wearing one of my running hoodies. Initially, I did this. This is the cat again, and it's showing the standard cat mood, which is obviously indifference to human beings. That's what cats always tell you. And the first time I talked about quantum, I had just about written a quantum program, but I thought I nearly went into that talk with pretty much this as the demonstration. And I said, you know what? I'm going to run an experiment on the cat, a quantum experiment, because I want to see if the cat can have multiple moods all at the same time. Sounds simple, so what did I do? I ran this experiment, and what happened? This is what happened. It turned out a cat can have 8 different moods at the same time. Okay. Takes a little time if you're not an English native speaker, that one. Okay. So, another quick demonstration. Let's get back to mirroring the displays. I'm getting good at this, aren't I? Back to here. Okay. Now, I have something called Clementines Cat. This is on my GitHub. Well, a version of this is on my GitHub, so you're welcome to go and get it. I think my GitHub link is on the next slide. What I've done here is I wanted to write a cat simulation that didn't involve killing the cat. So, here it is. I've actually got 2 simulations. Right, here's the first one, cat mood experiment. And they're illustrating 2 slightly different things. One of the use cases of quantum computers is you run an experiment, you get the result back, you adjust the inputs, you run it again. This is what we were doing to find the ground state of molecules. You have like a load of parameters, you put them in, and then the quantum score comes back and gives you a slightly better result, and you keep iterating on it. That's one use case that quantum computers are very useful for. So, that is sort of being mirrored in, no. And the other use case is that your quantum code will run itself just 100 times with the same parameters and then see what the most likely result is. And that's what's going on in this one. So what we're saying in here, this is the quantum code. We're saying for 100 goes, we're going to map all of the humans in my family. So we've got an array of 4 qubits here. Okay? The first qubit corresponds to me. The second qubit corresponds to my wife. The third qubit is Clementine. The fourth qubit is Felicity. What our cat does, and I'm sure if you own a cat, you'll appreciate this, the cat will come to me and ask me to feed her. Now, there's a 50% chance that I'll feed her. If I do feed her, she eats the food and then immediately forgets that she's eaten and then goes and asks my wife to feed her. Again, if she feeds her, she eats the food, the cat instantly forgets and goes and asks my daughter and so on. So, what we're doing here is, in this thing here, we're saying this line of code here, this is the first example of an abstraction that you mentioned here. So this apply to each thing will apply the Hadamard Gate to all of those 4 qubits. So that's a tiny little function, helper function that they've written in their library there. So we're applying the Hadamard transform to each of the 4 humans, and then we're just simply going to observe the value of the state. That's what this M thing does. That measures it and squashes the state. So it's either going to give us a 0 or 1. And then we're just going to count the number of times that the cat gets fed. If the cat gets fed 2 or more times, the cat's happy. If she gets fed less than twice, she's annoyed. So what we'll do is we will run this program. And again, if we come out to here, again, we have the C# program, which is the driver. And you can see we're just going to say, run the cat mood experiment and tell me how many times the cat was happy. So if we do this, what we should see is, I can't remember the maths. If you do the binomial theorem, I think it's something like, did I just do .NET Build or .NET Run there? I think I did .NET Build. Sorry, I meant to do .NET Run. And it will just run the same experiment 100 times. And you can see 70 times the cat was happy, 30 times it was sad. If I run it again, we should get a slightly different result. There you go, 73-27, and I can't remember the exact proportions, but it's binomial theorem. So that's a kind of, what we're doing there is running a simulation. And this is the type of simulation that people run against, say, weather forecasting. Just give us the most likely outcome using a quantum simulator. So they would run that weather forecast. IBM's working on this. They bought a weather forecasting company in America. I'm told that they bought that company precisely to test their quantum stuff on these weather algorithms. I don't know how true that is. And then the other use case, I'm just going to uncomment this code here very quickly. This is running a very similar thing, except the iteration now is outside of the quantum code. So it's going to go in and it submits the experiment once, checks if the cat's happy, outputs a message if the cat's happy, and then goes and does it again. So in this case, it's going in and out of the quantum program 100 times. So this is kind of mirroring the case where you would adjust the inputs each time and see what happens. So you can see it just does get happy outcome or get sad outcome. So we should be able to see whether, let's see what happens. All the outcomes will go there. There you go. And as you can see, sometimes the cat is happy because it's being indifferent to our feelings, and sometimes it's sad. It's still indifferent, but it's considering getting new owners. So there you go. That's Clementines Cat. Oh. Now, yeah, there's my GitHub link. If you're interested in getting that code, please feel free. And here's all the resources. This thing here, or is it this one? This is where you can get basically the Q#, download it, and run it on your own computer. You need the .NET framework installed, obviously, if you haven't got it. But it's all there. All the instructions are there. OK. So what are quantum computers good for? Standard Dilbert joke. I'll give you a moment to read that. I kind of felt like this the first time I did a quantum presentation. I felt like I was Dilbert in the, no, it's Wally, isn't it, this guy? And the guy on the left, pointy-haired boss, was the conference that was saying, where's your presentation, Birnie? We've talked about IBM Q Experience. Those are real quantum computers. You can use them. We've also talked about the Microsoft Development Kit, which I'm going to be focusing on trying to write more complex programs in this. But what else is going on in the world? I mentioned Rigetti. Sorry, this is Microsoft. 5 years. This was in March of last year. The guy that's head of quantum has said that they think they will have a working quantum computer in the cloud within 5 years. That's interesting. I know of a startup. I didn't have time to investigate it fully, but I was put in touch with a startup in America who believe they're going to have something within 2 years. Don't know how true that is. There is a company called Rigetti. They are said to have a 72-qubit working computer. And they have announced this, I think this is a marketing thing, $1 million prize. Now, quantum advantage is what they call it. What they're saying is, when somebody can come up with an algorithm on a real quantum computer that is better than a classical algorithm, that is quantum advantage. And Rigetti believe it's coming soon. So they're working on it. And Microsoft, I think, have got a very interesting technology. I had a meeting with a guy from UCL that was explaining this technology, which gives scalable qubit foundation. So what's it actually going to take to get a commercial computer? I shamelessly ripped this off from Microsoft's slide. Those are the foundation stones to actually getting something out there in the cloud. Now, these three things, scalable qubits, that's the physical hardware. The quantum classical interface, that is, how do you program your computer? At the moment, the IBM computer, the way that that works is the classical computer fires microwaves at single ions to alter the state of them. Okay? So, is that right? Yeah, fires a microwave at a thing that is suspended between magnets. Okay? And the reason why you have to do stuff like that is because a classical computer generates heat. Heat will destroy the information in your qubits. So that classical quantum interface is hard to do. Cryogenic systems, well, that's a solved problem. It's just expensive. You have to supercool the qubits. Otherwise, the information just leaks out. IBM has a marketing thing where they tell us that their real quantum computers are the coldest place that's ever existed. They claim it's colder than outer space. Didn't know that was possible, but there you go. Integration with cloud provider, well, as soon as the big players have it, they'll make that happen. I don't see that as a barrier. And algorithms and applications, well, that's already happening. I've written some, I've shown you some. I know IBM and a company in London called QBranch are already consulting. I've kind of touched on this. The guy in the slide there is an Israeli chap called Gil Kalai. He purports to have proved that quantum computers can't work, and I still haven't managed to understand his paper, but if you're interested, it's there. Right, so what are we using quantum for? This is Beijing, and they are using quantum computers, a company called D-Wave, to simulate traffic flow and to understand how to optimize traffic flow. That is being done right now. But this, I think, is the most exciting part. That molecule there is caffeine, which I think we're all familiar with. Caffeine is the most complex molecule that we can accurately simulate using a classical computer. Okay? If you build a classical computer that uses every electron in the universe as a bit, you still won't be able to simulate this molecule. This molecule is an iron-molybdenum complex, and I'll come back to that. But understanding the ground state of molecules is really important to understand how they interact with each other. So there is a lot of research going into really understanding how drugs work. For example, we don't know how drugs work. We make them work by trial and error, effectively. But if we could truly understand what I'm told is that what is really important is the exact juxtaposition of all the atoms within it and the angles of all the bonds. You can accurately simulate that stuff in a quantum computer. And that's really exciting. Why? Well, if you've heard of the Haber-Bosch process, it takes atmospheric nitrogen and creates ammonia for fertilizer. Bean plants do that. This is why crop rotation works. Bean plants can take atmospheric nitrogen and convert it into ammonia. They put it in the soil, and then your wheat takes up that. We don't understand how that works. In order to understand how bean plants do it with no energy uptake, we need to understand that iron-molybdenum complex on the previous slide. Why is that important? Well, This process, the Haber-Bosch process, currently takes 3 to 5% of the entire world's production of natural gas to produce fertilizer. So that's the potential. If we can understand these molecules correctly, perhaps we wouldn't need this type of chemical process. Unfortunately, I say unfortunately, the money is coming in from financial modeling. Big banks are already paying IBM and this company, Q Branch, I know this guy, to work with them to try and come up with algorithms for predicting the future values of the markets. And that was a talk I went to in London. There's the link if you're interested in that. Quantum Fourier Transform. I'm not going to spend too much time on this. This is fundamental to the last bit of the talk. If you go there, has anybody heard of the Fourier Transform? Yeah, classical Fourier Transform. It's used in digital signal processing. It converts the time domain into the frequency domain effectively. It squashes dimensionality down. Now, that's really important. Why? Well, I'm now going to talk about the elephant in the room, which is we're going to end on Shor's algorithm. Anybody know who these three men are? I'm going to guess not. You do? No. Good guess. But no. Those are three people that I doubt you've ever heard of. Next, do you want to take a guess at these two? I've got them in the wrong order, just to throw people off. They are, of course, Diffie and Hellman. Now, do you want to guess who these are? Yeah, Rivest, Shor, Edelman. How does public key encryption work? Well, I think most of us probably understand this. It relies on the fact that factorizing large numbers is impossible, or within it's of sub-exponential complexity for a classical computer. However, this is not true. There is something called Shor's algorithm that will factorize large numbers in polynomial time. And I have a demonstration of it. This is how Shor's algorithm works. First of all, there's a bit of number theory. I'm not going to go into this in too much detail, but step 6, this is a bit of number theory. It exploits that relationship, and I'm going to show you how I first came about this. I read Shor's algorithm in one of my books, and I wanted to demonstrate it and understand it myself. So I came to, I was on my way to work on the train one day, and I implemented Shor's algorithm in a, oh God, go away. Where's my browser? Where's my browser? Oh, there it is. That's not my browser. Oh, I have to stop. Oh, God. Excuse me. Where's my browser gone? There it is. Ah. In here. No, wrong browser window. Jesus. Why does that keep doing that? Huh? Ah, got it. Thank you. Thank you, thank you, thank you. Here we go. Here's a spreadsheet. What this is modular arithmetic. I was trying to factorize this number, 1,517. On this sheet, I've got started with 4. 4 squared is 16. 4 cubed is 64, and so on. And then in this column, I'm taking it modulo 1,517. So if you remember your number theory, that means that this function will repeat over time, right? So if you can find the periodicity of this function, that's the key to Shor's algorithm. Now, if I go down here, you'll see that it goes back to 1 there after 90 iterations. So the period of 4 with respect to 1,517 is 90. It turns out, I don't know why, but each of these things, I was trying to find a number that had a period small enough. This one was 45. They all seem to be multiples of 45. I'm not quite sure why. I wanted to find a number small enough such that, and 14 was my answer, that this has a period of 24, But crucially, 14 to the power 12 is a number that doesn't overflow. So there I'm able to exploit the relationship in the next stage, right? So this was my working on the train. So back to here. Okay. Well, how much time have I got? 5 minutes. Oh, God. Back to here. There's my spreadsheet. Here's the actual example. I suggest you take a photo if you're interested. And that tells us that the two factors are 37 and 41, and that's by using that simple relationship. Now, the key to Shor's algorithm is the fact that he worked out that using a quantum Fourier transform, you can find the period of the number in polynomial time. And the key point, the key realization is here that you don't actually care about what all those intermediate numbers are. You just care about the period. So the quantum Fourier transform transforms the function into the periodicity of it. That's an oversimplification. But again, it's on my GitHub. This chap is one of my colleagues. He helped me write this from first principles. So if you go to Andrew's GitHub, which I think is on the next slide, here it is. I ran my own algorithm, which I wrote in Q#, which is on my GitHub, which you can see that I factorized 7 and 3. And then, yeah, that's nothing particularly special. I'm sure you'll agree. Andrew then ran the algorithm, and he excitedly sent me this text one day saying that he'd found the factors of 35. Unfortunately, because classical computers are running quantum simulators, we lose the fact that it's not efficient. So Andrew said to me, so that's what it was. Now, why am I going through all this? Is Rsa dead? Well, yes and no. You will need a massive quantum computer which doesn't currently exist to expose Rsa and kill it off. Well, if Rsa is dead, well, there are solutions. There are already algorithms that will be invulnerable to quantum attack. And BB84, which is Bennett and Brassard, is demonstrably 100% secure. That is quantum key distribution. You can use a system of key distribution to make a one-time code to encrypt your message. That is 100% secure, provably 100% secure. Such systems do exist and are in use at the moment. Here's some more things. Andrew, my colleague, put me onto these things. They are different things that classical computers can do that are going to be invulnerable to attack. So why should we care about all this? Well, I'm going to finish on a quick history lesson. This is the amount of money that was said to have been invested in quantum computers in 2015 in millions of euros. This does not include government spending. And I think it's fair to assume that our government in the UK, Chinese government, Russian government, American government is investing billions in this technology. Now, why does that matter? Well, I'm going to go back to this history lesson. You remember these three gentlemen here? Well, oh no, sorry. So, Diffie and Hellman published their paper in 1976. So that's thought to be the start of symmetric key public encryption. 1977, Rsa was first published. Okay? So that's the history as we know it. Now, but, and this is where these chaps here come in. In 1997, the Official Secrets Act in the UK revealed that those three gentlemen there who worked for GCHQ in the UK already had these algorithms long before they were published by Diffie and Hellman and long before they were published by Rsa, Shaw, and Hadamard. So our security forces had this stuff already. Now, it is my contention that right now, as we speak, all of the Rsa encrypted stuff that we are sending around the world, which is demonstrably secure at the moment and cannot be broken by a classical computer, is being harvested by the security forces all over the world. All of your Rsa traffic is being harvested and is being kept. Because 5 years from now, when we have a working quantum computer, they will start decrypting it. So it's my belief that as tech leaders, we ought to be guarding against this right now. And that is kind of the elephant in the room of quantum. And that's all I have. Thank you very much for listening. Anybody got any questions, or should we just all go to the pub? Pardon? Oh, the carpet people. So this is a book by Terry Pratchett, which I read relatively recently. And in that, there is a group of people called whites, and they can see the future. And at the end of the book, what happens is they see this seeing the future thing as a curse, and it kind of starts getting into philosophy of the many worlds interpretation of quantum. And when I read the book, it resonated with me. Similarly, this thing here, The Garden of Forking Paths, these two books are sort of expressing things in terms of the many worlds interpretation, which I haven't gone into, but that's David Deutsch's belief that actually Shor's algorithm is said to, by David Deutsch, who's a British scientist, University of Oxford, he thinks that the fact that Shor's algorithm works proves that the many worlds interpretation of quantum is correct.
Because it's running it in multiple universes.
Exactly. Yeah. And that's how you get the resonance through the quantum Fourier transform is actually executing against all of the different values at the same time. So what it's doing is on my spreadsheet, it effectively gives you every row of the spreadsheet at the same time. And then the quantum Fourier transform gives you that. So yeah, according to Deutsch, that very algorithm, Shor's algorithm, proves that many worlds, it has to be correct. But obviously, we can't prove that. Okay, yes, sir?
I would think it would be maybe difficult to read all the qubits simultaneously, or how does that work?
So in Shor's algorithm, you only need to measure one qubit. If you read, to be honest, I haven't got my head fully around it. I've written the code in Q#. Andrew wrote a better version than me. My GitHub's got my first version, and Andrew's GitHub, which I think it was on a slide. If it's not, I'll put it somewhere. But Andrew's implementation was much better than mine. He actually implemented the quantum Fourier transform from first principles using Hadamard Gates and phase gates. So I asked him to do that because he wasn't working on a client project. So we do that at ThoughtWorks. I said, give me a grad. Grads are much better programmers than me. These young people that understand it all say, Andrew, I've got a job for you. Okay. Thanks very much, everybody. I really enjoyed it. Thank you.